Ever wondered how a computer can recognize your face or understand your speech? The answer lies in a powerful artificial intelligence technique known as deep feed-forward neural networks. In the simplest terms, a deep feed-forward neural network is a type of artificial neural network where information travels in one direction from input to output, with no loops or cycles. This network is deep because it contains multiple layers of neurons processing information between the input and output. Its history dates back to the 1940s, but it wasn't until the advent of modern computational power that these networks truly started to shine. Today, they are indispensable in a variety of applications, from voice recognition in your smartphone to anomaly detection in cybersecurity. At the core of these networks are the basic building blocks known as neurons. Each neuron takes in multiple inputs, applies weights and biases, and passes the result through an activation function to produce an output. Activation functions are vital as they introduce non-linearity into the network, allowing it to learn complex patterns. The architecture of a deep feed-forward network consists of an input layer, one or more hidden layers, and an output layer. The input layer receives raw data, the hidden layers perform computations, and the output layer produces the final result. Weights and biases in the network are initially set using various initialization techniques. They are then adjusted during the training process to minimize the difference between the network's prediction and the actual output. Training involves splitting the data into training, validation, and testing sets. The network learns from the training set, fine-tunes its parameters with the validation set, and tests its performance on the testing set. However, training these networks is not without challenges. Overfitting, where the model learns the training data too well and performs poorly on unseen data, is a common issue. Regularization techniques like dropout, L1, and L2, regularization can help mitigate this problem. Hyperparameters such as learning rate, batch size, and the number of epochs also play a crucial role in training. The architecture of the network, including the number and size of hidden layers, is another important factor to consider. Output. Despite their power, deep feed-forward networks do have limitations. They require large amounts of data and significant computational resources. The training process can also be time-consuming, and the networks can be difficult to interpret. Despite these limitations, the field of deep learning continues to evolve. Advanced architectures like convolutional neural networks and recurrent neural networks have broadened the applications of deep learning. Frameworks like TensorFlow and PyTorch have also made it easier to build and train these networks. Ultimately, deep feed-forward networks are a testament to the power and versatility of artificial intelligence. They show us that with the right tools and techniques, we can teach machines to understand and interpret the world in ways we once thought were exclusive to humans.